Welcome to this explainer. We usually think of the cosmos as this place of fixed, unchangeable destinies. But today we are exploring a completely fascinating disruption to the stellar life cycle. We're looking at an incredible anomaly, brand new data that completely challenges what we thought we knew about how certain celestial bodies evolve. It's basically the ultimate underdog story, giving a so-called failed star an unexpected, dramatic second chance at ignition.
Okay, let's dive into this. We often describe these particular bodies as being kind of caught right in the middle. Too massive to be planets, but too light to be stars. It's like they're doomed to exist in the cosmic shadows, right? They don't get the brilliant, blazing glory of our sun, but they also aren't rocky, terrestrial worlds like Earth. It's a really fascinating space to occupy, but sometimes the universe throws a wild curveball that changes a seemingly set fate.
Which brings us to part one, the fate of failed stars, and what actually holds them back.
So, to understand this new discovery, we first need to look at the baseline nature of a brown dwarf. This is a celestial object that forms from collapsing gas and dust, honestly, very much like a standard star. But here's the catch. It falls just short of the mass required to trigger sustained nuclear fusion. It just can't smash hydrogen and the helium in its core. And that lack of internal atomic ignition, that's exactly why they've earned the kind of unflattering nickname of failed stars.
To put that into perspective, we are talking about objects that range from 13 to 80 times the mass of Jupiter. I mean, think about that. Jupiter is already massive, and these things are up to 80 times heavier. They're absolute planetary heavyweights, but they still fall just a little bit short of true stellar mass.
Let's move on to an extreme cosmic duo and the groundbreaking discovery of ZTF J1239+8347. Now, what's really interesting about this slide is the dramatic mass transfer going on here. Located about 1,000 light-years away from us, right in the Ursa Major constellation, astronomers found a system that fundamentally changes the fate of these objects. You can see this intense stream of glowing matter literally connecting two brown dwarfs in a super-tight binary orbit. We are witnessing a spectacular mass transfer. One of these brown dwarfs is actively siphoning matter away from its companion. It's this violent, dynamic process that completely disrupts the usual quiet, isolated existence we associate with these bodies.
And to fully grasp the mind-bending scale of what we're looking at here, consider this. The entire orbit of this binary system, both of these massive 60 to 80 Jupiter mass objects, plus the space between them, would comfortably fit within the distance between Earth and our moon. That's it. It's an extreme cosmic dance happening in a space so confined it almost defies imagination.
This leads us to the theft of matter, or what you might call a vampiric lifeline.
Because these two massive bodies are packed so incredibly close together, there are some severe physical consequences. The intense gravitational interaction caused by their extreme proximity takes a really heavy toll. Basically, the sheer pull from the receiving dwarf causes the donor dwarf to swell up and lose its structural grip on its own outer layers. The donor essentially bleeds its gas, transferring matter that violently crashes onto the receiver. This creates a highly specific, superheated luminous impact zone. It's literally like a cosmic vampire feeding on his companion to grow larger.
Next up, the spark of fusion and reaching that critical threshold.
Now, this isn't just about one object getting a bit heavier. No, it's about a complete transformation of identity. Because both dwarfs are already hovering right near that 80 Jupiter mass limit, this vampiric accumulation is precisely the push the receiver needs. It's finally gaining the mass required to potentially ignite nuclear fusion. This cosmic feast is providing the ultimate second chance, pushing the receiver over the mass threshold so it can finally wake up and become a true shining star. And how did we even find this out? Well, we spotted this 1,000 light-years away because of a very precise 57-minute heartbeat. The superheated impact point where that stolen matter actually crashes onto the receiving dwarf pulses. It creates a distinct variation in luminosity that flashes exactly every 57 minutes. It was this rhythmic, mathematical echo in the dark that tipped off researchers that something wild was happening.
Huge credit for spotting this 57-minute blinking signal among literally billions of celestial objects goes to the Zwicky Transient Facility at the Palomar Observatory. The scientific detectives behind this were led by Samuel Whitebook at Caltech, and their groundbreaking findings were published in the astrophysical journal Letters. It is absolutely a monumental achievement in observational astronomy.
So, what does this all mean? Let's look at a common phenomenon soon and peek into the future.
While this is the first ever observation of mass transfer between two brown dwarfs, researchers actually suspect these vampiric systems might be surprisingly common. We just haven't had the right tools to easily spot them, until now. Excitingly, the upcoming Vera Rubin Observatory in Chile, with its massive survey capabilities, is going to be hunting for dozens more. This incredible underdog story might be playing out all over the universe as we speak.
It really makes you wonder, right? How many other failed stars are out there, quietly orbiting in the dark, just waiting for a dynamic interaction to give them their moment to become a sun themselves? It completely reframes how we look at the night sky. The universe is just this amazingly dynamic, evolving place, where even those cast into the cosmic shadows might just be waiting for their second chance to shine. Thank you so much for joining me for this explainer, and I absolutely can't wait to dive into our next topic with you.